to let you know, so the kind of work that I do, so I'm in the Department of Statistics and Applied Probability. So I do a lot of work in computational statistics and applied mathematics, which I hope is relatively kind of interesting for people here. What my talk is going to be on is on the multi-level Monte Carlo method, which originated actually in some work in operations research journals. So I hope that the presentation is of interest. And the kind of things that I've been doing in my career over the last few years is working on advanced computational methods, things like particle filters, sequential Monte Carlo, Markov chain Monte Carlo. And what I'm going to talk about is how these techniques could be used in this kind of very nice paradigm, which is the multi-level Monte Carlo method. I'll try to give you an overview of what it is as I go along. So just a brief kind of structure of this talk. So I'm going to do a review. I'll try to keep the level of technical content minimal, not because you can't handle it, of course you can, but I want to try to give a bigger picture of these methods. And basically there are three techniques which we've been working on in recent years, which is how to kind of expand this kind of framework into different contexts. And these are kind of three methods which I'll try to talk about time permitting. Okay, so this is, as I say, so it's recent work on this kind of so-called multi-level Monte Carlo. If you don't know what multi-level Monte Carlo is, I will tell you as we go along. And basically this is what it is. It's a methodology which essentially says if you have a kind of complex stochastic system, such as a diffusion process or a jump diffusion process or a partial differential equation, and associated to this process is some probability law, what it basically does is if you need to approximate expectations associated to this probability law, it will reduce your cost for a given level of computational effort, for a given level of error. Okay, so this is what it does. I will tell you a bit more about it. And basically the systems, of course, they arise in a wide variety of real applications. So diffusion processes you can find in many areas such as finance and engineering. But also these kind of methodologies are very important and useful in inverse problems which you find in weather prediction. Okay, so there's a wide class of problems where one wants to kind of consider these so-called complex stochastic systems, which I'll talk about. So there is a kind of need to use these techniques. And so basically the framework which I'm interested in, and so of course I'm trying to keep it in a kind of relatively non-technical terms. What you want to do is you want to compute an expectation or an integral associated with the system. Most importantly, we don't know how to calculate such integral in closed form. There's no such fast formula which is going to do it for us. And basically the system must be discretized in some way. So for instance, if you have a stochastic process in time which is continuous, you have to break up the time interval so that there's a discretization involved. Okay? And so the point is, in this kind of framework, the best what one can hope for is a numerical approximation of this discretized expectation. That's basically it. I mean, in a nutshell, this is what you want to do. So you say, I have this process I'm really interested in. I want to compute expectations with respect to this process. I can't do that analytically, and so I have to discretize the process in some way. Okay. So just let me give you a brief review of this kind of ideas. I'm sure that you're all familiar with these basic notions, but let me just say a little bit about it. So let's just start from the beginning. So for example, suppose that you're given a probability distribution pi, and you want to compute expectations of some class of statistics with respect to that probability distribution. So for instance, this could be the expectation of some random variable at a given time point. Okay, and I'll give you specific examples of pi and var phi as we go along. Okay, and I'm assuming that this integral cannot be computed in closed form. Okay, but so I must do some sort of numerical approximation. So one way to do numerical approximation, I'm not saying this is the only way, but this is one method which is kind of nice black box technique, is the Monte Carlo technique, which says if I can get capital N samples x1 up to xn from this distribution pi, I can approximate this integral by just the sample average of this function or var phi. So of course I assume that I can evaluate this statistic of interest. I just have to evaluate it from some collection of independent samples, IID samples, from this distribution of interest pi. Of course, I'm assuming from the beginning that I can do that. Okay, and there are, for a wide class of well-known probability distributions, methodologies for doing this exact simulation. Okay, So this is the standard Monte Carlo method. So let me just try to give you some examples of processes where this method, multi-level Monte Carlo, can be potentially beneficial in practice. So this is a well-known stochastic process in mathematics and statistics, which is the diffusion process, which basically says that you have a process at time t, so time is continuous, and basically you have some, on average, you're roughly like this, and you have some sort of diffusion like this, and then some randomness like this. So this is a Brownian motion, and this is, of course, the drift and diffusion coefficients, respectively. Okay, and so there's maybe some parameter theta. Let's suppose it's fixed. Just forget about theta for now. It's going to be used later if we have the time. So what would you be potentially interested in with respect to this distribution? So this induces a joint probability law on, for example, the distribution of the process at a given time t, which is real value. Let's suppose this is real value. So this process, for example, it occurs in finance. For example, you can rewrite the Black-Scholes model like this, and you might be interested in expectations of the random variable, which is a real value at time capital T, as for some function of var phi. So that happens a lot in option pricing, for instance. Okay, so that's an example of the kind of problem I'm interested in. And note that there are, of course, in some scenarios, one does know how to generate this process. There's a very famous paper, going back to 2005, Beskers and Roberts, which says that actually you can simulate exactly from this diffusion process. And of course, there are some processes where actually the diffusion law, the conditional distribution of x capital T given the initial position, which we suppose is known, is actually analytically available. But if the diffusion is sufficiently complex, exact sampling from this distribution x capital T is not possible. But in many ways, if I've managed to spell Moriana wrong, there are ways to approximate this process. And this is basic, so this is the one we're interested in, but you can take some, basically you can cut up the time interval from 0 to capital T in small instances, little h, okay, and you get this approximation to the diffusion. Okay, so it says that the process at time t plus h, where h is small, is roughly the position it was before, plus this additional term where the stochasticity z of h is a Gaussian random variable with 0 mean invariance h. Okay, and this process can be easily sampled given we know the initial position, which we'll suppose that we do. So you can simulate this process, okay, and then if you wanted to approximate this expectation, which I managed to press the wrong button, excuse me. So if I want to compute expectations like this, all I need to do is to just generate capital N samples through this system. So under some minor constraint, I'm just saying that you have the N times capital H, it gives you capital T, excuse me. So you just simulate this process, which can be done sampling IID Gaussians as possible, and you just compute this thing, okay? And as the number of samples gets very large, this gives you an exact answer, i.e. that with high probability, or in fact with probability 1, this thing exactly gives you back the expectation of interest. But there's a bias, because you've got a bias here. So this process is not the one of interest. Okay, there's been a discretization of time, and this bias is all associated to this kind of h. Okay, so if you're more familiar with ODEs or PDEs, it's like a little bit like finite inferencing. It's not quite like that. So there's a bias. So even if I have n go to infinity, I don't get back the true expectation I would if this process was the one of interest, which it isn't. Okay, so basically, what one can show is that in the limit, as the number of samples grow large, you get this thing, which is a biased version of the expectation, and this is the one of interest, and it's something like this. It's upper bound by something like this. In some, of course, there are some functions and some diffusion processes. So, of course, as h goes to 0, you get back the exact diffusion. So you can approximate it. Of course, you can't make h exactly 0 because there's some degeneracy there. But as h gets small, you get back the true expectation. So there are cars. Then, of course, if you know very well statistics, there's a kind of combination of two errors. So the two errors are: this estimate is stochastic. Okay, so it's stochastic, so there's an associated variance associated to that. And there's also a deterministic part of this error, which is the bias. And if you look at something called the MSE, the mean square error, which of course you will know, the mean square error is upper bounded by these two terms, which is something like this, which comes from the bias, because the mean square becomes the bias squared. So you get a constant times h squared, and this is the variance. Okay, and so you can see if the n, capital N, the number of samples you simulate, goes to infinity, this thing goes to 0. In h, you can't make it go to 0 exactly, but you could make it arbitrarily small. So somehow you can control the mean square error to an extent. Okay, so how do you control that? So if you give an epsilon greater than 0, less than 1 for some minor technical constraints, so what I want to do is I want to make the overall, the overall error, I want this to be epsilon squared. So I made basically my overall errors arbitrarily small. Okay, that's by choosing a h and choosing a capital N to make that arbitrarily small. So now if I suppose, let's just say for argument's sake, it's going to make our lives easy, that the discretization h is 2 to the minus capital L. Now if h is of order 2 to the minus L, if you rearrange the formula on the other side, if you let capital L be like this, then basically this bias squared, what do I mean by that? I mean this term, this thing is order epsilon squared. Okay, you can check the calculation, I'm sure you know that's not a problem for any of you. So that's going to give you that. Now if you suppose capital N is of order epsilon to the minus 2, the variance term is order epsilon squared. Okay, so that's very interesting. Now what's the cost to do that? So it turns out that the cost of simulating this procedure is the number of samples times 1 over h. So that's 2 to the L times epsilon minus 2, but 2 to the L, you can get it from this formula, gives you order to epsilon minus 3. So what am I trying to say? I'm trying to say if you want to make the mean square error of the ordinary Monte Carlo method arbitrarily small, i.e. order epsilon squared, the cost to do that is epsilon to the minus 3. Okay? And this is a kind of, this method has been around for many years. I'm not telling you anything new that I've done, this is just a review. Okay, so what am I going to do now? What I'm going to do is to tell you about this multi-level Monte Carlo method, which you may or may not be familiar with. And this methodology, what it does, is the only thing it's going to do is it's going to make, for some examples of course, there are examples where it's not going to be the case, is if you want the MSE to be order epsilon squared, the cost is going to go down. And that's what it is. That's all it's going to give you, and there are only specific scenarios where you can prove that's the case. Okay, and so that's what I'm going to describe to you now. And it's, again, for those of you who are specialists in Monte Carlo, it's like a bit like a control variant method. So the way it works is the following. So it's MLMC, multi-level Monte Carlo method, and it considers what's so-called a hierarchy of discretization. So remember that we had one discretization, we simulated it, and we computed the expectation. Now in this scenario, what you do is you suppose now I have a collection of discretizations h1 up to h capital L, where the first one, h1, is big, maybe arbitrarily big, and the last one is arbitrarily small, but this of course positive because I can't do anything. So, okay, so what is that going to give you? Well, I'm trying to describe to you what it gives you. Now this thing is the thing you're going to end up approximating, which is the expectation with respect to the finest thing. Okay, that's at some level, that's all you can do. Okay, and you can rewrite that as a collapsing sum just by adding and subtracting increasingly coarser and coarser discretization. So if you like, it's like you just have. So if you just have two discretizations, it will just be, so you just take the expectation of psi x at level capital L, where L is 2, and that's just the same as the expectation at capital L, minus the expectation at L minus 1, and plus the expectation at L minus 1. Okay, that's all I'm writing here. And that's not very exciting. You say, well, so what? What does this actual? So I've just written this thing in a special case where capital is 2. So okay. So I've rewritten the expectation. What utility does that give me? Okay, there are some minor technical constraints. It's not very important. So what can it do for us? So the idea is the following: is if, for instance, So if you look at this identity, it's not very useful. You say, okay, well I know how to approximate this one, I know how to approximate this one, I know how to approximate this one, so I just sample capital N samples, capital N samples, capital N samples, and most likely I get back nothing. And so the answer is, well, you don't get back nothing if you are a little bit clever about the simulation. So the idea is that if you look at the summand, this summand, here you have two probability distributions, a discretization at the finer level and the coarser level, okay, and that's the level of time discretization. Right, so now if it's possible to simulate a coupling, what I mean by coupling is a joint distribution such that the marginal in one coordinate is the coarse discretization and the marginal in the finer in the other coordinate is the finer discretization, then if I could sample IID from this coupling, I can approximate, I can approximate these terms like this, except that the terms are correlated, okay? And you can check some basic calculations that if I make them sufficiently negatively correlated, I can reduce the variance, okay? It's like a variance reduction. The question is, how do you do this? Well, I won't go into too many details, but the idea is that in this particular example, you could, I mean, just very quickly, just with a diagram. So the idea would be that if you recall that Euler-Murayama discretization, there was a kind of Gaussian random variable. So the idea is you have this one, so maybe this is the finest discretization. Okay, so you have to sample a noise here, a noise here, a noise here, a noise here. This is at time. Okay, so the idea is you just sample the noises, and if the hierarchy of the discretization is good enough, you just have to add these two noises together, for example, to get the noises for the other one. And the noises, I mean that by the Gaussian random variables. It's not very well explained, but the point is that basically I simulate one collection of Gaussians and I add them up together, and it so turns out that I get a sample from this so-called dependent coupling. Okay. Again, if you're a specialist in diffusion process, it's like you simulate a Brownian motion, and then the Brownian motion for this coarser one is the same. Okay. The details are not important, but the point is that you can do it. And if you do this kind of very funny dependent sampling, the variance of this difference actually is like order HL. Okay, and HL is that's important. Okay, so what is the procedure of this technique? All you do is for each pair of these expectations, with the exception of the first one. So the first one is just a single one, but for the pairs you sample from this coupling, and the first one you just do the ordinary simulation. And the number of samples you simulate is different per level. So you sample, first of all, you just do the ordinary thing at the most coarse level, and then for the couplings you sample NL samples. And the key point here is as the discretization becomes finer, so does the cost increase. So the idea is that the number of samples you initially sample is huge, and then the sum of samples you're going to simulate is going to go down. So the estimator just looks like this. So the first one you just do the ordinary thing, and then you have this so-called couple sampling. Okay, I mean again, there's kind of not too many details, but so you'll have to suspend your belief here. Okay, so now let's have a look at the mean square error of this method. So you've taken epsilon like this, and I want to make this mean square error of order epsilon squared. So let's suppose a discretization, HL is 2 to minus L. It's just so that I can illustrate the method. The bias squared is order epsilon squared in exactly the same thing. The bias is the same. You don't change the bias in this method. It's always, you're still approximating that finest discretization. Now, the variance, if you look at this expression, okay, this is just the sum of terms, okay, and they happen to be independent. So this is a sum of independent Monte Carlo estimators. And so the variance of a sum of independent random variables is just the sum of the variances. And moreover, the variance of these things, using this technical result, which I'm just mentioning here, which again, there are some technical constraints, is order HL. So what does it mean? It means the variance of this multi-level method is like this. And this HL is important because you've got that from the coupling. Okay, if you didn't have a coupling, this would be order 1, and actually the method is not actually potentially that useful. So it's very critical that you could get this correlation in simulation. Okay, so now I want to make this order epsilon squared at the same time. And the cost to do that, well, that's the number of samples I simulate at each level multiplied by the cost of doing so, which is associated to the order HL to the minus 1. Okay, this is a constrained optimization problem. I want to make this, I want to minimize the cost such that this is order epsilon squared, which of course, as you're all very well aware, is just standard Lagrange multipliers. Okay, so I want to minimize, I want to choose this to make the variance like this. Okay, and if you look, this is a nice paper by Giles in Operations Research in 2008. And it so turns out that you should choose NL like this. Okay, and if you then plug that into the cost is like this. Okay, so this is less than the Monte Carlo method for epsilon sufficiently small. So what has it done? So all it's done, so if, and of course if the diffusion is constant, actually you get something better. But that's less of interest because you can do exact sampling. So what's the point that I'm trying to say? If you want to get the same mean square error as the ordinary Monte Carlo method, you've got less cost. That's what it does, and it's a kind of very big method now, especially in applied mathematics. You know, this is a big kind of big business. People are very interested in using applying this multi-level Monte Carlo method in many applications. Okay, I'm trying to get, because I haven't got that much time, I'll try to get as much into the remainder of the talk as I can. So that's presented for diffusions, but it's useful in many contexts. So for instance, this is kind of, so I'm not a specialist in diffusion process, although I've been working with them a little bit, but they're very interesting. So for something called inverse problems are kind of something that came out of at least stochastic, the Bayesian ones that I know. You have a partial differential equation, you have a, for example, unknown but noisy initial condition, and then there's some associated data to that, and you want to infer the initial condition of the PDE, so that's called an inverse problem. That's one example of inverse problem. That's used a lot in weather prediction, especially in Europe and the US. It's also used in statistics. So there's something called approximate Bayesian computation. If you're a statistician, you may know that. But one of the critical points that I tried to kind of allude to is that the sampling of the coupling, you have to be able to induce this joint. So the key point here, as I said, is that these pair of samples, they're not independent, they're kind of sufficiently and cleverly jointly distributed. So the question is, in some of these examples, you have no idea how to simulate the coupling. You may be able to produce the multi-level identity, but you can't necessarily utilize this methodology in a kind of efficient way. In recent work, which I'm going to try to tell you about in the last 10 minutes of my talk, this has been relaxed. So you could try and do some methods which try to get around this problem. For example, if you can't simulate couplings, and in many examples you can't simulate couplings, you replace it with something which is called importance sampling and some other techniques, sequential Monte Carlo. There are also ways based upon approximate couplings and using Markov chain Monte Carlo, and the last one might be so-called coupling of algorithms. So I'm not going to go through the details of this. I have about 10 minutes, and I want to tell you a little bit about what I'm doing in this area, which is to try to enlarge the kind of number of applications of this technique in kind of practical examples. Okay, so let me just tell you one method. I think this one's the easiest one to describe, which is the importance sampling approach. Okay, so we have this multi-level identity. This is basically the thing that I wrote down a few minutes ago. It's just a kind of trivial collapsing sum identity. But the key point in what I tried to, when I was talking about diffusions, is there was a nice way of simulating a pair of random variables, x and y, whose marginal distribution was x was this one, the marginal distribution of y is this one, and that they're really suitably correlated in a kind of positive way, suitably in a positive way for the method, that is. So there's a kind of nice way to do that. But if you don't give me a diffusion, if you give me an inverse problem or a general PDF where there is some discretization and I don't know how to couple it, I don't know how to use a multi-level method, even though it might be highly beneficial to do so in practice. Okay, so this is we're in a time where we want to reduce our costs. So what I'm going to do is I'm going to consider this problem, but I'm going to suppose that the state space of this PDF are the same for every L. Okay, and there's an example I'll give you with that exactly there are many examples of that could be the case, but it's not the case for the diffusion example. So that does occur in applied mathematics. So just as I've explained a few minutes ago, if this posterior is a posterior of an initial condition of a PDE observed with noise, and the PDE is solved, e.g. by finite elements, and HL is scalar here. HL is scalar, so of course it's finite element, one dimension. But that's an example. And there are many examples you can see this reference to. Okay, let me just explain to you the problem, but probably this is the only problem I will be able to explain to you. So this is an example where multi-level Monte Carlo could be potentially useful, and then I'll show you how you can implement it, because we don't know how to couple the associated discretized distributions. So there's some PDEs, elliptic PDE. So I'm not a specialist in partial difference equations. Don't ask me anything about this. I work with the, once you give me, you give me the problem, and then I can show you how to solve it. But I don't know what this equation means. The key point is that there is some stochasticity in this coefficient. So this coefficient is like this, and these UKs are going to be random variables. So it's kind of like an elliptic PDE with random coefficients. And they are used, so I'm told reliably by my collaborators, that they're used in problems in hydrology and under some minor technical conditions. Again, I have to believe them, that there's a solution to this. But the key point is that this equation is used in practice. Okay, that's all I'm trying to say. I'm not trying to solve a problem which doesn't exist. In the first point. Now, in the coefficient, there were these UKs, so they're in some space, and I'm going to suppose that they're uniformly distributed. Again, this is not my model, so this is a work, actually this model that I know came from work of Andrew Stewart, who's at Caltech. And basically, these UKs, they determine a prior distribution for the U's. So the key point is that the coefficient and the PDE are random, and it's this quantity we want to infer on the basis of data, which I haven't explained yet. And again, what I'm saying, so this is a problem in applied maths, and this field frequently, or a lot of people who work on the numerical part of applied mathematics are now moving towards type of stochastic models, which one might have seen in statistics years gone by. Okay, so P is the solution of this PDE. What we assume is we have some data Y, which is the solution, so this is the solution of the PDE and some function of the solution, plus some Gaussian noise. Again, not my model. I'm just trying to explain to you. So data, solution, which the solution depends on these random U's, and then you have some Gaussian noises. Okay. And so the point is the following, is I'd like to sample from, or I'd like to approximate expectations with respect to my posterior, which is just like, this is the density of the Gaussian, of the posterior. Okay, so if you do Bayesian statistics, it's prior times likelihood is proportional to the posterior. Okay, this is the density of U given Y, so U is the randomness of you're interested in, Y is the data, and this is the thing you're interested in. But the key point here is, in order just to evaluate this function, which I don't know the normalization constant either, I don't know this thing, okay? The key point is, and even just to evaluate it, I need to solve a PDE, okay? And unsurprisingly here, the PDE is not soluble analytically, okay? But it so happens, of course, that some of you may be specialists in this, that you can solve the PDE numerically. And so what we will do is we will use something called the finite element method, which is basically a discretization of the problem. And let's say it's a discretization parameter, which is just univariate. But the key point, what is the point here? Well, how does this link back to what I've been talking about so far? Well, in many cases of interest, direct sampling from the PDE, the posterior associated to the PDE at any given discretization is not possible. So even if I forget about multi-level methods, I forget about this idea, just say, okay, I want to go do Bayesian inference, and Bayesian inference for statisticians over the years has said, okay, I have my posterior up to a constant, and I do my MCMC, and I can estimate expectations, right? This is what that field is all about, or at least was 10 to 15 years ago. And a lot of people use this Markov chain Monte Carlo method. But, okay, that would be all. No, or you can do some calculations, preliminary calculations, which tell you that if you use this multi-level technique, you're going to reduce the cost relative to doing even MCMC or Monte Carlo. Okay, you can show it mathematically, but the problem is we don't know how to, well, we don't know how to construct couplings of these consecutive discretizations. I'm not saying it's impossible. I'm just saying that if you give me this problem, or if you give it to somebody who's a specialist in stochastic simulation, they don't know how to do that right now. Of course, maybe the problem may change. So, in order to do this MCMC method, you need to know that there's a distribution of interest up to a constant, so you don't even know the coupling. So the point is, it's hard to implement this ML method, which is going to give you some computational savings. And the idea basically is to kind of modify this multi-level identity and use what's called importance sampling. Okay? So basically, assuming that you know each distribution up to a constant, which in this example you can, the expectation of this functional with respect to the finest discretization is the coarsest one plus this thing. Okay, and what is this thing? Well, don't worry about what this expression is. It's just an expectation with respect to this distribution. Okay, and then these are some of unnormalized densities, and these are normalizing constant, and this is the function. Okay, it's just rewriting the expectation, where instead of you having a difference of expectations, it's just an expectation with respect to one of these distributions. And there's some details here if you want to check it. So what's the utility of this thing? Well, the utility thing of this thing is now if I can simulate from this one, and I can simulate from this sequence, and I can approximate these normalizing constants, well, you could then apply the multi-level technique. Okay, so that's exactly what this slide says. If you could sample from these guys and you could compute these ratios, you can approximate this. And it so turns out that in fact there's an algorithm to do exactly this. So this, before I ever knew anything about multi-level Monte Carlo, I knew a little bit about this method, so we were involved in this article 3, which is called Sequential Monte Carlo Samplers, and it does exactly that. Okay. And it basically just generates a collection of samples in parallel and sequentially approximate these things at these ratios. So you can do that. It's an advanced stochastic simulation method. So then I'll just make one remark because I haven't got much time here. So the complication with this is analyzing the variance, because basically this method is now basically what I'm trying to say is that when you approximate these summons, in the ordinary Monte Carlo method, they were independent with respect to each L. That's no longer the case when you use this so-called advanced method, sequential Monte Carlo method. And we've overcome that in some work. Okay, well, I'm not going to hope to finish, so I think I've only got 2 minutes anyway before post questions. So maybe I will just skip to the summary because of the time constraints. I would like to have said a lot more, but the key thing that I was trying to get across in this talk is that the multi-level method is a kind of beneficial. It's a cost reduction technique. You can use it in many applications, but once you broaden the kind of scope of those applications, the kind of nice method, that nice coupling scheme, the kind of funny diagram I drew is no longer there, and you then have to try to look at designing methodologies which can try to expand upon this technique. Of course, if you set in time discretization or univariate, but there are examples where the discretization is in multiple dimensions, and we're working on contributions in this area. And that's all I have for you. Well, if I want to finish on time, that's all I have for you. Thank you very much for your attention.